This will be recorded just for anyone who's not actually here attending right now, so that I can send it to them afterwards, so that everyone who's been involved gets the same information at the same time. But I'd just like to say thank you for joining us today and being here, and thank you for your submissions to the student competition. So we are doing the ceremony today, so we're actually going to find out which one of these teams and which one of you is successful enough to win the TecQuipment 2025 Student Competition. So I just want to start off and say thank you to all the teams and institutions that entered the TecQuipment Student Competition. I know it's a bit of extra workload for you to do alongside all your studies and exams, but being able to provide this for us, it means we can showcase what you're doing as students, what your institution is doing, and how you use our equipment to further your engineering education. Now, there was a wide variety of entries that used a variety of equipment from our fluid mechanics, dynamics range, and our materials testing and properties range. The standard of entries this year on a whole was really high, and when we scored all of the videos together, on average, there was only 1 point separating the winners and the runners up. Now that's insane. We've not had it where it's been that close of a competition. So it just goes to show how good and how high caliber your videos actually were, and that's amazing. So how we like to go through this, we like to provide a bit of feedback and show the videos that did well, a little bit of feedback performance, and then we actually go through who are the top videos and then our actual winner. So videos that did well this year, they introduced the equipment and the experiment really clearly, so straight from the offset, we as judges could tell what we were going to learn in that video, what equipment was being used and why. There was really clear background information. So as I just said, right from the start, we knew what this video was going to be about, so we could sit back and listen and really enjoy the videos. So they also critically analysed the results that were presented. So sometimes when you're doing tests, it doesn't always go perfect. It doesn't always go according to plan. And videos that did really well kind of highlighted what went wrong or why, or the possibilities of this. Because in real life, in engineering, nothing is ever perfect, even though we wish it were. Also, the best videos showed and demonstrated using the equipment, and it was a really easy step-by-step process. So even though us as a company, as judges, we know our equipment, so we know what it does, what it can be used for. But when these videos are published, the public won't, so having that step-by-step process really makes it easier for anyone who doesn't know the equipment to follow along and really understand what that video is about. And lastly, the best videos related to real-world situations and real-world usage, because the reason we have practical teaching equipment is because we want you to be able to use that equipment and go into the real world. So by being able to do that within this video, showing that real-world application, it goes hand in hand. So, a little bit of feedback for improvement to make sure that your videos are even better next year, so it makes it an even tighter margin for us to judge. But if you do these improvements, it will make it 100% better. And that's having a clear outline of what the presentation will be about and its purpose. As I said in the good video feedback, there was this continual line of, this is what's going to happen, this is how we're going to use it, this is the results. And that really made it easier for us as judges. As I said, some videos did really well explaining the potential errors or critically analysing their results. Other videos were less so. So just a note for any future users. Methods also allowed for a higher accuracy, but some still had sources of error. So you just have to be very careful with your videos to really pinpoint what the accuracy is and why. Okay, so for this bit, these are the videos fighting for the TecQuipment 2025 Student Competition crown. We're going to watch both videos, and then at the end, we're going to reveal who the winners are. So this is video number 1.
Welcome. We are Claire Ramsey and Matthew McDevitt from York College of Pennsylvania, studying civil engineering. Together, we're excited to present our research on the influence of weir-nose geometry on broad-crested weir hydraulics. Water is one of our most vital resources, and managing its flow is critical for both communities and ecosystems. Broad-crested weirs are essential hydraulic structures used in dams, spillways, and flood control systems. Broad-crested weirs control water flow to prevent floods, ensure steady water supply for various needs, and protect communities by managing downstream speed and volume. But not all weirs are the same. Small design variations, such as shape of the nose or its radius, can significantly impact how water behaves as it flows over the crest. These differences affect the flow velocity, water levels upstream, and even the efficiency of water discharge. Our experiment focuses on these geometric differences, specifically how varying the nose radius of a broad-crested weir changes the flow characteristics in a controlled channel. To answer our research question, we designed an experiment to study how the nose radius of a broad-crested weir affects the upstream head, flow velocity, and discharge coefficient. We utilized the 2.5 meter flow channel, a hydraulic bench, and 3D printed weirs with different nose radii. In our experiment, we tested 6 different nose radii for the broad-crested weirs: 0, 10, 25, 40, 75, and 100 millimeters. When water flows over a broad-crested weir, fundamental energy and continuity principles govern its behavior. The surface level drops as water accelerates onto the weir crest due to the narrowing flow area. The total head H combines static and velocity heads above the crest, as described by the continuity principle and Bernoulli's equation. Real-world factors like friction, turbulence, and non-uniform flow cause energy losses. These are captured by the discharge coefficient C, which adjusts the theoretical discharge equation to calculate the flow rate Q. We then vary the weir's nose radius and flow rates to achieve different upstream heads, aiming to see how geometric changes impact water flow efficiency. To start our experiment, we connected the hydraulic bench's outflow pipe to the flow channel's inlet pipe, turned on the pump, and adjusted the flow rate to achieve specific targets, recording them with the bench's flow meter. We tested multiple weir shapes, some with no radius, other with nose radii of 10, 25, 40, 75, and 100 millimeters. For each weir, we focused on measuring water depths at specific points under controlled flow conditions. First, we placed the weir into the flume, centering it carefully. This position remained the same for all weirs for consistency. We measured the upstream water depth by using a depth gauge at a fixed spot on the water surface, then calculating the difference between this measurement and the upstream reference height. Next, we used the depth gauge to record reference heights. These measurements, taken at the start, middle, and end of the weir, serve as our baseline for comparing water depths during the experiment. We then measured the water depth at the surface at the start, middle, and end of the weir crest, relative to its corresponding reference height. To ensure reliability, we took 3 measurements at each position and repeated this process for 4 different flow rates. After testing one weir, we replaced it with the next weir shape. We repeated all steps, recording reference heights, adjusting flow rates, and measuring water depths. By keeping our methodology consistent, we ensured reliable comparisons between different weir shapes. The top graphs showing upstream total head and depth above the weir crest versus discharge illustrate that the smaller nose radii result in higher head and depth. This trend leads into the bottom graphs where the discharge coefficient, represented by the slope of the trend lines, increases with larger nose radii, improving hydraulic performance over the weir. This next graph illustrates the relationship between discharge and upstream velocity for different nose radii. Similarly, as expected, the graph shows us that larger nose radii consistently lead to higher upstream velocities for the same discharge. These graphs show how different nose radii on broad-crested weirs impact velocity distribution at different flow rates. Consistent trends appear across all configurations, with minor differences due to the changing nose radius. Overall, our findings confirm that the larger nose radii improve flow by reducing resistance. At low and high flow rates, the nose radius weir had a 4.9% and 6.08 higher upstream head difference than the 100 mm radius weir. Upstream velocity for the 100 mm radius weir was 16.4% and 16.1% greater at low and high flows respectively. The discharge coefficient using total head was 8.61% higher for the 100 mm radius weir, aligning with expectations. Larger nose radii improve weir efficiency, reducing resistance and enhancing water management. Slight measurement variations in environmental factors could affect results. In conclusion, larger nose radii enhance hydraulic performance by reducing resistance and increasing upstream velocity.
So, that was our top entry from York College, Pennsylvania, and now we're going to see who they are fighting against for the top spot.
Hello everyone, today we'll be taking you through our submission to the TecQuipment Student Competition. I'm Jonathan Hutchins.
And I'm Ian Charlton.
And we are second year undergraduate mechanical engineering students at Southampton Solent University.
We are excited to present our project, which was developed as part of our engineering materials module under the supervision of Dr. Tahan. We will be answering the question, can we identify unknown materials using mechanical properties in experimental testing? This is important because in industry, safety, and verifying your suppliers are common concerns, and recycling is an ever-growing need.
The tech equipment that we're using today is the SM1002 benchtop tensile testing machine. On the right side we have the small course adjustment wheel for setup and a large wheel with a 50:1 gear ratio, which is used during tensile testing. Between the chucks we've placed a long specimen for use with the optional extensometer so we can calculate the Young's modulus. To find the ultimate tensile strength of our materials, we need to use the short samples without the extensometer fitted. Data is measured by the load sensor and displayed on the digital load meter. The extensometer dial gauge is connected to VDAS software, where we input the sample dimensions and record the data from both the extensometer and load cell. This allows us to calculate the stress and strain.
This is how we'll approach the research question. We'll start with pre-test measurements before moving on to the testing. Then we'll analyze the results and use the results to try and identify the materials. Finally, we'll use several methods to verify our findings. To help narrow down the possible materials in the database, we calculated the density of each sample by using the volumes and the masses. By using the density formula, we were able to identify a key physical property that supports material identification.
Across our three samples, a behaviour called necking is exhibited. This is where the material plastically deforms beyond the maximum tensile strength before fracture, causing a reduction in cross-sectional area. In the stress-strain graph, this is where the curve begins to fall off from the peak.
Initially, we struggled to measure the elongation and reduction in cross-sectional area of fractured samples with a caliper, as we need to reassemble them. To rectify this, we used two alternative methods.
The first method was image analysis to calculate the reduction in area. We used the images captured during tensile testing and, using a known measurement, captured the pixels per millimeter and applied that scale to the unknown measurement. This was more accurate.
The second method was using analog gauges. The gauges are pictured on the right, and it was found that the elongation gauge was more precise for measuring elongation. However, image analysis was more accurate for measuring reduction in cross-sectional area.
We measured the tensile strength of short samples, and in our tests we observed variation in results. Some contributing factors such as machine accuracy, material defects, and slight misalignment during clamping added to the variation.
An extensometer, along with the longer samples which are pictured on the right, were put into the tensile testing machine, which was then brought to a set force to ensure we stay within the elastic region, the data for which was used to calculate the Young's modulus.
We compiled our data comprising of the material density, Young's modulus, elongation percentage, and ultimate tensile strength in this table. We used the ANSYS Granta Level 3 material database of metals to identify our sample materials by applying the limits. In the case of material A, we found it must be a variant of carbon steel or stainless steel. For material B and C, we reached a much more conclusive selection of brass and aluminium.
In material A, we observed a classic cup and cone fracture, which is a clear indicator of ductile failure.
A faint cup and cone shape is present, but it's much less pronounced than in material A. The tooth-like features around the edge suggest a mix of ductile and brittle behaviour. This aligns with the properties of brass, which has moderate ductility but can fracture more abruptly under certain conditions.
The break shows a distinct angled shear plane and relatively clean surface, with little necking. This suggests a relatively brittle failure under shear. Even though aluminium is generally considered ductile, the behaviour could be influenced by work hardening or surface flaws in the sample.
As an extra step, we tested the magnetic properties of each sample to help narrow down the material types. This was especially useful in distinguishing between carbon steel, which is magnetic, and austenitic stainless steel, which is generally non-magnetic.
We can conclude that the method used was successful in identifying materials.
However, other testing methods are required for higher accuracy on the specifics of material processing and grades.
Thank you for your time and consideration. I've been Ian.
And I've been Jonathan.
So, those are our two videos. The first one from York College, Pennsylvania, and the second from Southampton Solent University. And they are going to be fighting for the overall winner of TecQuipment's 2025 student competition. And I'm sure you're all dying to know who it's going to be. And as I mentioned earlier, there was only 1 point difference when we averaged all the scores between the judges, between these two videos, which showed just how good and high caliber that they were. So amazing work to both teams and everyone else involved in their videos. But for now, let's crown our 2025 student competition winners. And they are, round of applause, it's the team from Southampton Solent University. Your video managed to get 63.5%, so an amazing score. And as I said earlier, it was the fact that you used great visual and video elements, and it was such a cohesive video, and it was generally, we loved watching it. So congratulations. You will be the winners of £1,150 and a custom-made TecQuipment trophy and certificates for you to show off and show that you've been a part of this competition. And yes, well done, Ian. Woohoo indeed. And honestly, it was great work and it was such a good video, and I believe it was only a short amount of time between you actually submitting it as well. So the work you managed to put into it was brilliant. But also a round of applause to our runners up, who, as I said, 1 point difference, so 62.5%. But all the other videos involved were really high caliber this year. So I definitely would say a round of applause to everyone who submitted the videos. They are great pieces of work to really showcase the use of our equipment and your insights and your learning into engineering. So, again, congratulations. I will stop sharing now. Congratulations, and we will be in touch with the winners, and also for those who weren't involved on this call today, we're going to send out an email just so that everyone involved knows that Southampton Solent University won TecQuipment's 2025 student competition. I'm going to end that there today. Thank you so much for taking the time to come and be on this call with me and find out our winners. Have a great afternoon, everyone. Well done, Jonathan, and well done, Ian. Have a good rest of the afternoon, everyone. Bye.